All right, we're back. We are on note 6, page 2. Yeah, note 6, page 2. We're talking about the direct comparison test. The tricky part about the direct comparison test, as I illustrated last time, is making sure that what you want to happen happens, basically. So if you think that a series diverges, the series that you're direct comparing it to better be smaller than it, and it better diverge. If you think a series converges, the series that you're comparing it to better be bigger than it, and it better converge. That's what really is the tricky part. You need positive term series, so you can't have a series that's sometimes positive, sometimes negative. I don't know, the camera's having trouble like keeping up with me right now, and I don't really know why, but that's all right. So here, we would be in trouble if this was just cosine of n, because sometimes cosine of n is positive, sometimes it's negative. Direct comparison test doesn't really deal with that, but we're in luck because cosine squared is always going to be positive. So here, I'm going to build this a little differently. So I think this is basically going to look like 1 over n squared. I think basically. So what I need to do, though, is establish a couple of things. So first, I know that this numerator here is definitely somewhere between 0 and 1. Like it has to be. So I'm going to say 0 cosine squared of n. I mean, it could be 0 because I mean, cosine can be 0. So like maybe sometimes this magically is 0. It's actually not because cosine is never 0 at an integer value, but whatever. But this is definitely true. So then that means that, 0 over 1 plus n squared is less than or equal to cosine squared of n over 1 plus. So this is true because 1 plus n squared is always positive, right? So we're not like changing any signs by doing this. I'm literally just dividing through by 1 over 1 plus n squared. Or I'm dividing through by 1 plus n squared. I'm multiplying everything by 1 over 1 plus n squared. Doesn't really matter. Okay, so this is definitely true. So I know at this point that like this sum is less than this sum. Now what I need to do, though, is I need to show that 1 over 1 plus n squared converges. So let's see what we can do there. 1 plus n squared is definitely greater than or equal to n squared. Let's say for n, I mean, for n greater than or equal to 1 for sure, and we're going from 1 to infinity, so why not? So this is true, which means that 1 over 1 plus n squared is less than or equal to 1 over n squared. And that's really good because we know that this series, the sum of this is a convergent P series. So that converges. So let's see what we can do. We can say that the sum of cosine squared of n over 1 plus n squared is less than or equal to the sum of 1 over 1 plus n squared, which is less than or equal to the sum of 1 over n squared. And I guess they're all greater than or equal to 0. Okay. Now, so we're just trying to show that this converges. We're not going to know what it converges to, and that's something you just have to kind of either get used to or get over, because we're just never going to know. So here, we're basically done. I'm going to say since the sum of 1 over n squared converges, p equals 2, which is greater than 1. I'm just going to say, well, I guess I'll say 1 over 1 plus n squared converges by direct comparison. I mean, I could have used like the transitive property, right? Like if then, whatever. And so does the sum of cosine. So this one might be the most complicated one we've done so far, but it's still not bad. I mean, they're usually pretty straightforward. Usually, they're either like straightforward or super annoying. Like those are kind of your two options. Let's take a look at this one. So this one you can definitely overthink. And I say that because I always overthink this. I'm looking at this and I think this probably diverges. I don't really know off the top of my, like immediately looking at it, I'm not sure if this diverges or not. But then you start to think about it a little more. And maybe you think, like we know something about the natural log of n, right? So kind of like this. And so this would be 1, because the natural log of 1 is 0. And then at e, the natural log of e is 1. So I'm going to say for n greater than e, the natural log of n is greater than 1. And that's important, because if the natural log of n is greater than 1, then we know that the natural log of n divided by n is greater than 1 divided by n. And the sum of 1 divided by n is the harmonic series. I don't know, I said that really weird. The sum of 1 over n is the harmonic series, and that definitely diverges. So we have a series that's bigger than a divergent series. It must diverge. So I'm going to now say, since sum of 1 over n diverges, and I'm going to say it's harmonic. You could also say it's p equals 1, which would make it diverge. So harmonic, the sum of natural log of n over n diverges by direct comparison. So this one, the way that I personally overthink it, not that you need to know how to overthink something, I'm sure you can come up with your own ways to overthink things. I always think like natural log of n, like should I be getting like some kind of like a Taylor polynomial for that maybe, and then like dividing by n and seeing like what's happening? I don't know. I just like in my mind I'm like maybe I compare this to somehow like 1 over n to the 1/2, because it's like natural log, I don't know, natural log of n feels sort of like something. Could just straight up do the integral test, except this is about the comparison test. Left to my own devices, I would definitely have done the integral test on this. Make u equal the natural log of x. Then you get 1/2 natural log of x quantity squared, and then that definitely diverges. So knowing multiple ways is useful because it gives you just more chances to, even if the directions say use direct comparison, it's like you can't really decide how to do that until you decide if you think it converges or diverges. So you have to like have a guess to begin with. So whatever, I don't know what I'm talking about. All right, this one's gonna be straightforward-ish. I'm thinking geometric, right? So for n greater than or equal to 1, n plus e to the 2n is definitely greater than or equal to e to the 2n. And 1 over e to the 2n is geometric, and so that's good. So therefore, 1 over n plus e to the 2n is less than or equal to 1 over e to the 2n. And I'm going to say that this is equal to 1 over e squared to the n. And I'm saying that because it makes the geometric series like a little more obvious, I guess. So let's say since the sum of 1 over e squared to the n converges with its geometric r is 1 over e squared, which is definitely less than 1. So since that's true, we know that 1 over n plus e to the 2n converges by, what the, that's not a b at all, by direct comparison. And we got it. All right, so it's a good test. I like to use it. You'll see it on the AP exam, they will frequently just set it up for you. They'll be like, 0 is less than or equal to a sub n is less than or equal to b sub n, and you know that a sub n diverges. What do you know about b sub n? Something like that. Like it's way more straightforward than actually like coming up with your own series and things like that. But you should be able to do it, especially on like problems like these. I think you would have basically no issues. It takes a little bit of practice though, but there's like millions of problems you can find on the internet. We're going to learn another test that we can use. Also, I should say, I mean, are there other ways to do all of these? I don't really know, but could probably use the integral test on a lot of them. Certainly on E, I probably would have used the integral test. Who knows? But anyway, be back in the next video. We're going to learn another test, so I will see you there.